It's a good idea at this point to summarize the products from the main reactions we cover in this chapter. As we discussed, the aldo reaction typically gives you a beta hydroxycarbonyl, or if you dehydrate it, you'll get an alpha beta unsaturated carbonyl. Another reaction we discussed was the Claisen, or the intramolecular version, which is the Dieckmann reaction. That typically gives you a beta ketoester. The Michael reaction, or the Stork reaction, which is the enamine version of the Michael reaction, generally gives you a 1,5-dicarbonyl as a product. Let's now review some of the reactions we covered in this chapter. In the first reaction, we're using a 1,3-dicarbonyl. We're adding base to it and then mixing it with an alpha beta unsaturated ketone. In the next example, we're going to use an enamine, or we could use a ketone plus LDA, which is a base. And then we're going to mix either of those two with an alpha beta unsaturated ketone. In the third reaction, we're using a ketone and an aldehyde plus base, and then we're heating the reaction. In the last reaction on this slide, we're using an ester, adding LDA to it, and then mixing that with another ester. The first example here on this slide is an example of a Michael reaction, and we can tell that from the fact that we're using a 1,3-dicarbonyl and an alpha beta unsaturated carbonyl. Base would remove one of these protons in between the two carbonyls. That carbon would then attack the beta carbon of this alpha beta unsaturated carbonyl, leading to the formation of this bond here. The product should have, like all Michael reactions, a 1,5-dicarbonyl. So if we count the carbons from one ketone, from the Michael acceptor, to one of the other carbonyls from the Michael donor, there should be 1,5 to each other. In the next example, we're going to use either this enamine or this ketone with base to attack an alpha beta unsaturated carbonyl and do a Michael reaction. So the enamine is nucleophilic at the alpha carbon. A ketone, if we add base, would remove a proton from this carbon, which would make that carbon nucleophilic. In either case, that carbon, either from the ketone or from the enamine, will attack this beta carbon, leading to the formation of this bond. This is the beta carbon of the Michael acceptor. This is the alpha carbon. The next example is an example of an aldo reaction. So if we use a ketone and we add base, we should remove one of these protons. Because the ketone is symmetrical, it doesn't matter. Then that ketone, that enolate from the ketone, would add to this aldehyde. Notice this aldehyde does not have alpha hydrogen, so it can't form an enolate. So the ketone enolate will attack the aldehyde, and after dehydration should form a double bond there. So we're forming this bond here initially, turning this aldehyde into an alcohol. So you'll have an OH here initially, but then we lose that OH plus a hydrogen here, and that's the reason why we have a double bond instead in the product. In the last example, we have an ester. If we add LDA, it should remove an alpha proton from here. That carbon will now attack the ester. So this carbon would attack the ester, eliminate the methoxy group to give you a ketone that is beta to the ester that we use as an enolate. So this is the ester that we're starting with. So that would be this ester. It's just drawn a little bit different. We want to make a bond between the alpha carbon to the carbonyl of this ester. In the next question, we want to use an enamine, and we're going to react it with this alkyl tosylate. Enamines, remember, are nucleophilic at the alpha carbon. In the last question for the summary, we want to do a synthesis of converting this ester into a 1,3 keto ester. Enamines are nucleophilic at the alpha carbon, and they're essentially an equivalent, or they're equivalent to enolates. And so just like enolates, if we add an alkylating agent like this alkyl tosylate, this carbon will attack the carbon with the leaving group. So this carbon will attack here, displace this tosylate group. We're going to form this bond here in the product. And now the enamine under aqueous acid should be converted into a ketone. In the synthesis example, we're going to start off with an ester and we want to make it into a beta ketoester. That sort of screens the Claisen reaction. So remember, if we take an ester and we add base, we can do a Claisen reaction that typically gives you a beta ketoester. So keep that in mind. So in this example, we can use this ester that we're starting with, add base, and add an ester that is going to allow us to add the component shown here. All right, so our original ester is this one here. And from the alpha carbon, we're going to make this bond to an ester. Eliminate the leaving group, so the leaving group gets eliminated here when the alpha carbon attacks that carbonyl. So that gives us the ketone you see at the bottom of the slide, the keto ester that we see at the bottom of the slide. Then to add the double bond in between the two carbonyls, we can add base and formaldehyde. So this carbon would turn into an enolate, it would attack this carbon, and after dehydration, we would get a double bond there. And so that would lead us to the final product. Here's another example of a synthesis involving condensation reactions. So we're going to start with an ester, and we're going to end up with a beta ketoester that has this functional group here, this cyclohexyl group plus the nitrile. In this synthesis problem, we're going to start off with an ester, and we're going to turn it into a beta ketoester with a methyl group, and also we will add the cyclohexane that has a nitrile on it. To access the beta ketoester, we can do a Claisen reaction. So adding LDA to the ester will turn it into an enolate at the alpha carbon. That carbon can then attack the appropriate ester to do a Claisen reaction. So we can replace the methoxy group and end up with the beta ketoester that you see down here. So the right side up onto this carbon is our original ester. The left side is the ester that we added as a second substrate in the first reaction. If we add base to the beta ketoester, that should deprotonate the most acidic hydrogen, which is this one here. That would turn it into an enolate. And then we could add an alpha beta unsaturated nitrile through a Michael reaction. So the enolate will attack this carbon, get rid of the double bond, turn it into a enolate here, or enolate-like structure here, which then gets protonated by water or some acid in at the end of the reaction. That gives us access to this intermediate, which then we can turn into the final product by doing a methylation. So adding base would deprotonate the most acidic hydrogen, which is this one here, in between the two carbonyls, and then the methyl group will be added by adding methyl bromide.